again. Welcome back for another week of anatomy and physiology and crazy stories that just happen to go with what I'm teaching today. And if you thought last week's stories were crazy, don't worry, I have more. And especially at the end of this group, just like I said. Then again, a lot of you guys already work in the healthcare fields. Um, or going into the healthcare fields. So maybe you've got some crazy stories about things. Feel free to add them in the forums if you've got some. I always enjoy learning new crazy medical stories. So feel free. So today we're going to talk about breathing. So we talked about digestion. Now we have to talk about the other half of getting things into our body that we need to live, which is oxygen. And as you can see, Monty's back and crawling around my neck. He just had a good shed. He actually got most of it off himself, very good, and now he's warming up around my neck. So if I have to loosen him a bit to breathe, you might see that because he's giving me a bit of a hug. Don't worry, this is a normal thing with him. If he's cold, that's the only time he tightens up around my neck. He never gets angry or anything like that. It's just he wants to snuggle and get warm, and he doesn't realize, yeah, the neck is also where I kind of need my blood going through to my brain, and the breathing bit usually isn't so much the breathing that he cuts off when he gets a nice tight hug like this. It's half the time it's the blood. So I have to remind him to be nice to me, and usually if I just gently pull on him like this, he realizes he needs to lighten up. So that's don't worry, he's not choking me out. Actually, he's gotten tight, but he's never gotten to the point of choking me out. That, and like I said, I've had him for going on 18 years now. So yeah, he just snuggles when he's cold. So he's like, where's the summer? Why isn't it warm? So anyway, so speaking of breathing, let's go ahead and talk about breathing, because we need the oxygen for a lot of reasons. One of the reasons being, turning it into ATP along with everything we eat. So if you remember, ATP plus oxygen plus glucose equals ATP and carbon dioxide. That's just breaking down cellular respiration to its completely fundamental. It's actually a little more complicated than that. And we did touch on this last semester in 168, if you recall, going over cellular respiration, but a lot faster than you would in a biology class. So remember, before we get to how we breathe, let's take a moment to define respiration itself, because technically there's actually like 5 respirations going on in your body, depending on what's going on. And we have a different name for each one. But the one I just talked about, cellular respiration, is just one of the respirations happening in your body right now. So, first one, movement of air in and out of the lungs, commonly called breathing or ventilation, which is why if we put somebody on a ventilator, it's breathing for them. Actually, we're going to get into a really interesting, crazy weirdness that can happen very rarely, especially when people are put on ventilators. And blood coagulants. So it's kind of interesting. We'll get to that at the end of this section of notes. So anyway, the exchange of gases between the air in the lungs and the blood is called external respiration. So in other words, getting those oxygen molecules across cell membranes so that way it can get into our red blood cells and then move it around the body for all your cells that desperately need it. And then the transport of gases between the air in the lungs and the body cells is another form. Also, the exchange of gases between the blood and the body cells themselves. So again, the red blood cells are bringing it around. Body cells are going, oh, please, I need some oxygen. And the red blood cells deliver it. That would be called internal respiration. And then last but not least, the one that hopefully has been, scientifically banged into your head up until now is cellular respiration, where then the cells take that oxygen that has just been delivered to them, hand it over to the mitochondria, and the mitochondria goes through the 3 steps actually it only has 2 of the steps in the mitochondria, the first steps in the cytoplasm, to make ATP, which is called cellular respiration. So, we're not really going to go over cellular respiration in this chapter. We're more interested in ventilation, external respiration, and that's the two things we're really going to zoom in on. How do we breathe? Why do we breathe? And it's actually kind of clever because it's a pressure differential that we use our diaphragm to actually fill our lungs and then kick it back out again. So we actually use pressure. Yeah. So again, the cellular respiration, I'm just going to touch on it here. The reason we need to eat and breathe is to keep us alive, and we need that, we need to make energy to do that, and that energy is in the form of adenosine triphosphate, or ATP. Like I said, if we break it down to brass tacks, it's basically the oxygen we breathe in, the carbohydrates that we break down into glucose, and then we send that to the mitochondria where it takes and it ends up in carbon dioxide, water, and energy in the form of ATP. So again, there's the 3 steps: glycolysis, where the glucose comes into the cell. It's broken down by the cytoplasm. You get 2 ATP out of that. Then you go through the Krebs cycle. This is where oxygen is needed inside of the mitochondria here. And then you get 2 ATP and carbon dioxide out of that. And then last but not least, the electron transport chain, which resets the Krebs cycle and uses oxygen. And then at the end of resetting this sucker, you get 32 ATP and water. So for a total of about 36 to 38. Now, keep in mind, that's a pristine number. We make more or less depending on factors and all sorts of different things, but that's the highest you can go is 38, but usually it's around 36 to 38 depending on what's going on. Okie dokie. All right, so again, that was just a crash course in that real fast because we want to talk about this. So our respiratory system is split into 2 tracts. You got your upper respiratory tract, which is basically your nose, your nasal cavity, your sinuses, your pharynx, and if you've ever had sinuses stuffed with having a head cold or whatnot, or yay, allergies, then you've felt your sinuses before, not in a good way. And then you got your lower respiratory tract, which is your larynx, your trachea, your bronchial tree, and your lungs, which are really cool in themselves. And there's a part that we don't talk about, but is actually really important to breathing, is your diaphragm. He's basically the muscle that helps you kind of move when you take in a deep breath, the diaphragm is actually pulling down, which actually makes the lungs suck in oxygen. So it's actually a kind of a cool pressure differential, which is actually can screw us up when we're climbing up really tall mountains, which is why you see people who go up the crazy tall mountains like Everest. I'm sorry, I'm not a big fan of going up, I like going up on top of our mountains. Of course, they're ancient and old and worn down, so it's a little easier. I love our mountains, but risking life and limb to get to the top to Mount Everest, and you may feel differently about this, and that's fine. It just makes me go, really? And did you know that Everest is actually the biggest open-air human graveyard in the world? Because of all the people that try to attempt it and fail, and we can't take the bodies back down because it's too dangerous to go get them, so we just kind of leave them there? Yeah. Fun. So, no offense, I really don't want to be frozen to the side of a giant mountain for the rest of my eternity after death, so I prefer to be cremated and shot into space. It's easier. You're probably going, there's no difference in that. I'm like, yeah, there is in my mind. But then I'm crazy, so Anyway, so let's talk about your nose. So you got your nose, which are called your external nares, or your nostrils. So if you have that power to flare your nostrils really good, then they're your external nares. So next time, walk up to somebody and go, look at my external nares. And I'm sure they'll go, what? And you'll be like, Anyway, so bone and cartilage with internal hairs. Why do we have the internal hairs? It traps large particles, aka filters the air. You're going to notice this a lot. We filter the air big time up through our nose and our nasal cavity because we don't want things getting in. So, our first line of defense is our nose hairs. However, unfortunately, sometimes they get to the point where they're, growing out your nose, which if you have a mustache, you don't notice, but for those of us that can't grow a mustache, yeah, you kind of notice. Although I don't understand why some people just wax them. That makes me ow. Just trim them a bit. Anyway, but still, you need nose hairs. Nose hairs are your first line of defense, and then the mucus pretty much behind that. We want to filter out anything getting in, especially things like fungus, because unfortunately fungus, once it gets in, it's really hard to get back out again. We have antibacterial drugs. We have, antiviral things like vaccines and everything, fun stuff like that. But antifungal, yeah, if it's in your body, the problem is the fungus is an eukaryotic cell, just like us, whereas, bacteria is a prokaryotic cell, which it can die from things that, won't kill our cells. But to take out a fungal infection is basically, we don't have the drugs to differentiate between the two of them right now, and unfortunately, if you get antifungal drugs, they're also anti-U drugs, which is why we have nose hairs. It's why we have earwax. It's why we have mucus. So we have these things to keep, not only bacteria and viruses out, but also fungi, because they're not fungis when they're inside your body. Laugh. Monty, wasn't that funny? Okay. Anyway, so bone and cartilage lined with mucous membranes. Again, this has two fold purpose. One, it warms and moistens incoming air, because we want the air to be nice and warm and moist. I know, and some people hate that word, but sorry, it's the only thing I can. It's wet. Anyway, damp. It's damp. There we go. There's another word. Nobody freaks out about damp. Anyway, I think. So it's warm and damp. The reason we make it warm and damp is we don't want to hurt the tissues in our lungs. If you've ever been out on like a cold day or, gone up north to go skiing or something like that, or anything, it's like a really cold day, it kind of hurts to breathe, especially if you're doing a lot of physical exertion out in cold days with dry air, because that really does, that's again why we have all this, because we want it damp, we want it warm and damp, so we don't really make our lungs go ow. So we got to protect our lungs. So first, that's what we have, the mucus, and second, as I mentioned, same thing with the nose hairs. It's to protect us from things coming in, so hopefully we're screening things out, so therefore we don't have to deal with them. And olfactory reception, which we did talk about. Again, if you had 168 last semester, at the end of the semester, we did talk about that. There's basically a patch of sensory cells pretty much right here, and they're about the size of a quarter, and I've had people that unfortunately have had it damaged and they can't smell anymore. So yeah, be nice to your quarter-sized nose receptors. Anyway, and they're also resonant chambers for speech. So like, I'm sure you've probably heard people sit there and say, yeah, when they speak they're so nasally, or when they sing they're so nasally, and yeah, that's true. It's like, I can't sing, so but if I cut off my nose, I sound different, like this. And I think we all kind of can do that. So that's actually why we need our nose too, because it helps us enunciate. And it's weird when I do that and talk for too long. Anyway, so, and speech is really interesting. We're going to touch on it here as well. So anyway, so we have nasal conchae, which is turbinate bones, which are right here, and right here, and right here. So you have a superior at the top, you have a middle and an inferior. Again, these divide the nasal cavity into a series of groove-like passages. Again, to catch more things coming in, we want to filter the air as much as possible, so that way, if we can catch it then, we don't have to deal with it later with our immune system, you know what I mean? Save energy. So increases the turbulence of incoming air. Again, this is twofold: A, to catch things, and B, to make it warm, dampen, and filter it. So that's actually why we have these grooves, so that way the air gets all groovy-woovy up in here and gets, thoroughly filtered, warmed up, and dampened before we breathe it in. So, again, why do we have these things? That is why. So anyway, sinuses. So they're paired and lined within 4 skull bones, or frontal, ethmoid, sphenoid, and maxillary, and then they drain into our nasal cavity. And we all know how much that fun is when it's draining way too much when you're sick, and you're like, and you can feel them where they are. So anyway, why do we have them? A, it actually reduces the weight of our skull. Our skull is huge, especially if you look at other, mammals, and because we have big fat brains. That's just across the bear as humans, we have big fat brains, and we have big fat heads. And especially go, look at your cat, look at your dog, or look at Monty. Of course, he's a reptile, but still, his head is not big and fat because his brain is the size of a pea. But we have to deal with big fat head, and if our skull wasn't punched through with a bunch of holes in it, then it would be really, really heavy. And that would make our necks even have to work even harder than they already do, having to keep our head up. So it reduces the weight of the skull. Also, it's resonating chambers for speech, because we are a very speech, oriented species. And it's interesting, a lot of our facial features are actually, because we're such social creatures, we actually, if you ever wondered why humans have the white of our eyes, it's actually because we're extremely social and we talk to each other a lot. We like looking at each other's eyes. Now, I'm saying, in some cultures it's not, it's very rude to stare at somebody's eyes. But a lot of other animals take direct eye-to-eye contact extremely negatively. That's why I learned very early on when I was working at the zoo, never make direct eye-to-eye contact with any primate. They take that as a challenge of their authority. So you kind of look to the side, but that's why they don't have whites around their eyes. You only see animals' whites around their eyes when they're freaking out, especially in the mammal. And being raised in a horse barn, I assure you, and I was, which is funny when people go, "Were you raised in a barn?" I can actually say, yeah, I was, actually. But, when a lot of animals freak out, they'll roll their eyes, like, when dogs freak out, they go, and you can see the white of their eye, because that usually means they're freaking out. So, yeah, don't stare at any monkeys, apes in the eyeballs. You're directly challenging their authority, and they're going to fight you. And FYI, they're usually stronger and crazier and insane. I know. I worked with them. Anyway, but yeah, we have the whites because that actually lets us know where we're looking when we're looking at each other. So we can tell if we're paying attention to each other by looking at, where we're looking, and the whites of our eyes give that away, which is actually really interesting. So if you wonder why, a lot of other animals don't show the whites of their eyes, but they have them, that's one of the reasons, is because actually it gives away where we're looking, and, it helps us with social cues. So just in case you wanted to know why we have the white of our eyes, there you go. Because we're extremely social. Right, Monty? He's not. Snakes are not extremely social. Monty's just chill. So, yay. Anyway, learn the pharynx, or the throat. So it's a wall of skeletal muscles lined with mucous membranes. Again, it's a passageway for air and food. We just talked about the food half of it, last week, and now we're talking about the breathing half of it this week. So it's a resonant chamber for speech sounds. It comes in 3 parts. You got your nasopharynx, which is the uppermost behind your nasal cavity, your oropharynx, the middle behind your oral cavity, and your laryngeal pharynx, which is your lowest part. And so let's talk about that part right there. So 9 pieces of cartilage, all hyaline except elastic cartilage of the epiglottis. So we have thyroid cartilage, which is your Adam's apple. Us ladies don't have one that's very pronounced. You guys get the bigger one. Yay. Epiglottis closes off the airway during swallowing, unless you're gifted like me in the fact that you, can talk so fast that you swallow your own spit and then choke on it, because I'm gifted like that. That's why they tell you stop talking while you're chewing, so you don't choke. Anyway, and there's 2 parts of vocal folds, which you got your false vocal cords over your true vocal cords. And this is really cool. We normally use our true vocal cords to talk, but there's actually musicians, especially Tibetan monks, that have trained themselves to use both sets of vocal cords, and they do a type of singing with it. So I want to show you a quick clip of that right now.
A few moments later.
you go. They are doing two notes at once. Is that not insane? Anyway, I just think that is just the coolest thing since sliced bread. Anyway, actually, sliced bread was actually a pretty cool thing too. I was just watching something on the history of bread and when it was actually starting to be pre-sliced for people, which was kind of fascinating actually. Anyway, before I completely get off track, so yes, you actually can use both sets of vocal cords to sing, which is actually kind of cool. So it takes a bit of training, and apparently there's 30 billion uh, things showing you on YouTube now for that. So if you're a singer and you want to try for something cool, check that out. Anyway, the glottis, that's a triangular slit opening between the two pairs of the vocal cords. Then you've got the cricoid cartilage, which is basically a ring of hyaline cartilage attached to the first ring of the trachea site. It's usually the site of a tracheotomy, so if you have to go in and put the tube, intubate them, because for whatever reason they're not breathing and you need to just bypass the whole mouth part. Yeah. And those of you that have done it, you are amazing. Again, my mother was a EMT paramedic and saved many, many lives up in New York. But that just amazes me. Anyway, so arytenoid cartilage, corniculate cartilage, cuneiform cartilages. So there's a lot of cartilages going around, keeping so it doesn't collapse. Because the last thing you want is your larynx to collapse. It's kind of weird. So again, voice production, mucous membranes form two pair of folds. The upper, which is the false, and the lower, which is the true. The triangular space in between is the glottis. So sound originates from the vibration of the vocal folds themselves. Other structures, the pharynx, the mouth, the nasal cavity, and the paranasal sinus is convert this all into recognizable speech, which is why, when we get skulls and we try to do a reverse thing with dinosaurs, we try to figure out, how did they sound? And we've done that. We've kind of gone in and kind of reverse, put in a lot of the tissues and whatnot that we thought were there, pertaining to, following the notches on the bones where things were attached. And we've actually produced dinosaur sounds just from, trying to reverse engineer and see if that's what they sounded like. So it's always fun with dinosaurs. We're always trying to reverse engineer. But anyway, here's a picture showing you of everything. So you've got your larynx right here. You've got the cartilage that is supporting it. And then again, you've got the trachea. Now the trachea has 16 to 20 incomplete rings. So they're all C rings. So in the back, they don't touch all the way. Again, it's to give, some give. Again, we usually don't have completes around here. So anyway, so there's 16 to 20 C rings, which may or may not be a test question in the future. The rings are completed by the tracheus muscle and the elastic connective tissues facing the esophagus. And it's lined again by mucous membranes. Got to keep that air coming in warm and wet. Again, it also has a lot of cilia, that's pseudostratified columnar epithelium. So if you looked into it, it'd be the pseudostratified, which means they're kind of like, and they have cilia on them. Again, they're catching things, trying to catch as much as possible before it gets to the lungs where everything's kind of vulnerable. And then we've got the cornea, which is basically the point where the trachea divides. So into the right and left primary bronchi. But the reason they have these things is because we don't want this to collapse. I don't know if you've ever played with tubes before in your life and you're trying to blow up a tube for your kids or your younger siblings or whatever, or you've tried to blow it up yourself. You know how it is when it collapses, and especially if it's wet on the inside, it sticks together. We don't want that, so that's why we have these cartilage rings, so our trachea doesn't collapse, because we need to get the air in all the time, every time, And if it suddenly goes and gets stuck together because it's all warm and wet in there, and the last thing you want is, yeah, that. So, not good. So that's why we have all these C-rings, to keep it open for the breathing, because that's important. Now, I like to think of the lungs kind of like a funky upside down tree, because they really are. And you're going to see why I say that in a bit when we get to the end of these notes. So the trachea comes down and it splits into the left and the right. And that starts further splitting and splitting and splitting and splitting and splitting. And so we go from the primary bronchi to the secondary bronchi to the tertiary bronchi to the smaller bronchi to the bronchioles, which are very, very tiny. And then that splits into the terminal bronchioles, which goes into the respiratory bronchioles, and then they're covered in these sacs. And that's pretty much what your lungs are made up of all these sacs, and are called the evoli, or just one of them is an evoli. All of them are the evolus, and they're also known as the evolar sac. So your lungs are really just a whole bunch of bubble wrap. That's kind of how I see it. Unfortunately, just like bubble wrap, they can pop, and that's not good. We'll get into World War I and why that wasn't good in just a moment, because unfortunately World War I really, really, really came up with ways to attack people's lungs, which was not cool. Of course, war just isn't cool anyway, but still. Anyway. So, long story short with cheese, so all these little holes. Now keep in mind, these, they're not holes, they're sacs, and all these little sacs are actually connected to one another. So not only do they have holes going into basically the respiratory bronchioles that basically go into these, but they also connect to each other. So there's like a whole, looks like a bunch of grapes, but imagine a bunch of grapes that are actually all interconnected as well. So again, why? Surface area. We have lots and lots and lots and lots of these guys. They're all interconnected. Surface area. Remember, more surface area always gives us more places to absorb. And these guys are very, very thin-walled. They only have like 3 layers, I think. And that's because oxygen needs to be able to flow freely into the blood, and then carbon dioxide needs to flow freely out. So the less layers between that, the more it's going to happen, which we're going to get into. So again, lungs are basically paired, cone-shaped organs enclosed by the diaphragm and the thoracic cage. It's surrounded by pleural serous membranes. Again, so we've got the visceral pleura covers the surface of the lungs. The parietal pleura lines the thoracic cavity, and the pleural is lined with a thin layer of serous fluid, because it makes those two layers work as one and gives it, double strength. So, it's kind of like when you're ripping out saran wrap and you've accidentally, because I can't get saran wrap to work. Is it me? I don't know. My mom can make saran wrap work. I can't. I pull it up and it instantly goes, and then I can't pull it apart again. So I guess I'm just useless. Anyway, so yeah. So basically that's what it does, is that liquid between the two parts makes it go, and then you can't pull it apart. So it gives it double strength and a lot of elasticity to it. So the pleural fluid has a very high surface tension that allows the two membranes to act as one. And the right lung is bigger than the left lung. Our right lung is always bigger than our left lung. And you'll notice that the right lung has 3 lobes and the left lung has 2 lobes. Yeah. Why? I don't know. But here's a fun fact. Monty here, he does have 2 lungs, but only 1 lung can work because of just how much is packed into his body. The other lung is actually atrophied in a little wet lump. So even though all snakes have 2 lungs, they only have 1 working lung. That's why a lot of snakes die of respiratory illnesses, which is why I'm very, very careful with Monty to make sure he doesn't get a respiratory illness, because that can knock out a snake pretty quick. I actually did buy a friend for him a long time ago. I rescued her. She was in a bad way, and I thought I did everything correctly, and she died, and I am sad. And it was unfortunately of a respiratory illness, which a lot of people, especially they sell the baby snakes in stores, and especially Monty's type, and they're really, really sensitive, and they're hard to keep alive unless you know what you're doing. That's why I get a little annoyed when snakes are sold at such a young age, because they're Of course, then again, a lot of people have issues with different people selling pets. But that's what it is. Anyway, so before we end this half of the things and actually get into how breathing works, we're going to talk about lung clots because I thought this was bizarre. So occasionally what happens is some people can get a clot that's a reverse cast of the lung and they literally can cough it up. And then you get an inside look of the lung from just a blood clot. These are blood clots, although this is more of this is kind of like mucus and blood clot. But literally, these are blood clots that somebody coughed up. They're very floppy and very fragile, but at the same time, is that not insane? This was this is actually the more recent of them. This made the news, I think 5 years back, maybe. This was out of a 36-year-old male with end-stage heart failure. They put him on a pumping machine. And the problem is the pumping machine and, like I was saying earlier, ventilators, if you don't dial it in just right, it can actually do more damage than good, because it actually puts a lot of pressure on everything. So, unfortunately, this made his blood clot up. Even though he was given anticoagulants to kind of stop against this, but yeah, pumping machines can force your blood to clot big time, so they pump you full of anticoagulants. But even despite that, he still horked this up. Unfortunately, he didn't make it. He did die. I think it was like a couple of weeks after he horked that up. So it wasn't like this killed him. This did not. It was his end-stage heart failure that killed him. But he horked this up. Is that not insane? I mean, look at that. It's like a perfect reverse cast of the inside of the guy's lung. Then this one was from a 34-year-old woman with an airway infection due to diphtheria. She died a week later. This woman survived. She was a 25-year-old woman who was pregnant, had a disorder, clotting agents, but she horked that up, and then she gave birth, and she's fine, and her baby's fine. Weird. So I just wanted to show you that, yeah, sometimes we can get a literal clot of your entire lung, and we hork it up, and then we get to look at it and take pictures and submit it to scientific journals and go, oh, that's cool, and move on with our day. So, kind of crazy. So I just wanted to show you that, yeah, isn't it neat? I'm sad that 2 people, unfortunately, did not make it. Of course, they were already really, really sick when this happened, but this woman did. She's fine, living her best life now with her baby. Just happened to happen, and she just had one heck of a pregnancy because it aggravated her clotting disorder. So, whew, crazy. All right, so next time we're actually going to talk about actually breathing and how that works. So, and I'll see you in just a bit.